Alright, so in this example we have a stationary block A having a mass of ma, which is struck by a bullet B having a mass of mb. B has a speed of vb1 before impact, and during the impact the bullet passes through block A. Block B has a known speed of vb2 after exiting the left side of A. We're also told that after impact the speed of A is unknown. Block A continues to slide to the left post-impact on a rough horizontal surface which has a coefficient of kinetic friction of mu k. Block A eventually comes to rest after sliding through a distance of d. Based on the given information, we're asked to determine the distance d traveled by the block after impact. Okay, so to help us out here, what I'm going to do is I'm going to try to define two distinct events. I'm going to try to define an event, or I should say maybe three distinct instances in time, which define two events. I'm going to define a time 1 immediately prior to impact. I'm going to define a state 2 immediately after impact, and I'm going to define a state 3 after the block has moved a given distance. And so what I'm going to do here is I'm going to assume that essentially the bullet transverses through the block in a very small amount of time in comparison to the time it takes for the block to move a distance d. Now the reason for that is I don't want to have a lot of extraneous forces acting on the system while the impact is taking place, and so that's a very important assumption to have to do what I want to do. In this regard, if I draw a free body diagram for the system, if I look at it just between states 1 and 2, for the system I'm actually going to have simply a normal force. We're going to assume that the block's not moving, and so I'm not going to have to worry about friction in this case. And we'll have the collective weight, which I'm just simply going to call W. And so in this regard, I'm going to assume between 1 and 2 that we don't have to really worry about the friction force here causing much of an influence. In fact, maybe I should put it in there just for the sake of completeness. But note that I'm not going to worry about this at the instant because I'm going to assume the block's not moving. If I look between then states 2 and 3, I'm now going to look at just the block alone actually. And what I'm going to look at here is say when the block's sliding, I'm going to have some friction force holding it back F. Again, I'm going to have some normal force, and here I'm going to have some weight. So how am I going to do this? Well, again, I'm going to make the assumption that friction does not cause an impulsive load. And maybe I'll add to this the word here because this is a limited assumption to this problem. And so if this is true, and I define, for example, a coordinate x to be positive to the left, then I can say that linear momentum is conserved in the x direction in this scenario. And so in this case, what am I going to have? Well, I'm going to have that the initial momentum of the system prior to impact in the x direction is going to be m of the bullet times vb1. In post-impact, I have the bullet flying freely with mb and vb2, and then I'll have the mass of the block post-impact with a speed I'll call va2. If we look at this, we realize quite quickly that va2 is my only unknown, and so I can solve for that, and I'll have that va2 is going to equal, in this case, mb times vb1 minus vb2 divided by the mass of block A. I can then take that information, now that I know the post-impact velocity of the block, and I can apply the work-energy equation for just the block. And if I do that, I can say that T2 plus V2 plus U2 to 3, non-conservative, is going to equal T3 plus V3, where 3 will define the state where the block has finally come to rest. So in this regard, I can say that T2 is going to be the kinetic energy of the block post-impact, which of course is going to be 1/2 times the mass of the block times Va2 squared. I can define a datum to be through the center of mass of all of these objects, and so that's exactly what I'll do up here. And if I do that, then I'll have that V2 is actually going to equal V3 is going to equal 0. I can also note that there's no non-conservative loads interacting with the system between states 2 and 3 other than friction. So here I'll have the integral from state 2 to state 3 of the friction force, which is going to be minus F in the I direction for the value I've shown here. I'll dot that with a differential displacement dx in the I. And so what I'll get here is simply minus F times the distance traveled, which is d. And then finally I'll have T3 is going to equal 0. If I take these pieces of information and add them together here, what am I going to get? Well, I'm going to have 1/2 times the mass of A times VA2 squared minus F times D is going to equal 0. And so I can use this and solve for the distance traveled D. D is going to equal, in this case, MA times VA2 squared divided by 2 times F. So I need to find my friction force. To help out with that, I'm going to start by summing forces in the y direction on the block and noting this is static. So I'm going to have this as N is equal to the weight of the block, which is going to equal MA times G. And then I'll know that F is going to equal, in this case, mu K times N, which will be mu K times MA times G. And so what I'll be left with here is the distance the block travels post-impact will be given by MA times VA2 squared divided by mu K times MA times G times 2. You'll note that the mass of the block cancel out, and so what I'll have here is D is equal to VA2 quantity squared divided by 2 times mu K times the gravitational constant G. From here you can plug in numerical values and wrap this problem up. I know you got it, everybody. Take care.